These planets smell like rotten eggs. And that disgusting detail just solved one of the biggest mysteries in astronomy. For 20 years, scientists couldn't figure out what these massive worlds actually were. Now, thanks to the James Webb Space Telescope, we finally have an answer, and it came from the stench of sulfur. 133 light-years away, in the constellation Pegasus, there's a star called HR 8799. It's young, only about 30 million years old, practically a cosmic infant compared to our 4.5 billion-year-old sun. And orbiting this star are 4 enormous gas giants, each one between 5 and 10 times the mass of Jupiter. These aren't just big planets, these are monsters. But here's the problem that's been haunting astronomers since 2008, when these worlds were first directly imaged. Nobody could figure out how they formed, or even what they truly are, because at these sizes, the line between planet and failed star starts to blur. Were we looking at genuine planets, or brown dwarfs, those strange in-between objects sometimes called failed stars, because they never quite ignited fusion? The answer matters more than you might think, and that's not even the strangest part. To understand why this matters, you need to know how gas giants are supposed to form. There are 2 competing theories, and they paint very different pictures of cosmic creation. The first is called core accretion. This is how Jupiter and Saturn formed. A solid core slowly builds up inside a disk of dust and ice around a young star. It collects rocky material, icy particles, solid chunks of matter, until it becomes massive enough to start pulling in surrounding gas. Think of it like a snowball rolling downhill, gathering more snow until it becomes an avalanche of hydrogen and helium. The second theory is gravitational instability. Here there's no patient core building. Instead, a swirling cloud of gas around a young star simply collapses under its own gravity, almost instantly forming a massive object. This is closer to how stars form, and it's how brown dwarfs are born. No solid material required, just gas collapsing into gas. So which process created the HR 8799 planets? Were they born like Jupiter or like failed stars? For 2 decades, scientists couldn't tell. Carbon and oxygen, the usual chemical fingerprints, weren't helpful because they can come from either gas or solids. The planets were too far away, too faint, hidden in the overwhelming glare of their star. These worlds are 10,000 times dimmer than HR 8799. Imagine trying to see a firefly hovering next to a searchlight from 100 miles away. But here's what no one is talking about. The James Webb Space Telescope changed everything. A team of researchers from UCLA and UC San Diego developed entirely new data analysis techniques to extract the incredibly weak signals from these distant worlds. And when they finally decoded what Webb was seeing, they found something remarkable. Hydrogen sulfide, the same molecule responsible for the smell of rotten eggs. Now you might be thinking, so what? Planets smell bad. Big deal. But that sulfur is the smoking gun. Here's why. At the distances these planets orbit from their star, 15 times farther than Earth is from the sun, and beyond, sulfur can only exist in solid form, not gas, solid particles, tiny grains, rocks. There is absolutely no way these planets could have accumulated their sulfur as gas. It had to come from solid material in the protoplanetary disk, which means these planets must have formed cores first. They had to sweep up solid matter, heat it up through gravitational compression, and vaporize those solids into the gas we're detecting now. In other words, despite being 5 to 10 times more massive than Jupiter, these giants formed exactly like Jupiter. Through the slow, patient process of core accretion, they are definitively planets, not failed stars. And this is where it gets really interesting. The implications go far beyond just categorizing 4 distant worlds. This discovery completely reshapes our understanding of how massive a planet can actually be. The traditional cutoff between planets and brown dwarfs was about 13 Jupiter masses. Above that, an object can briefly fuse deuterium, a heavy form of hydrogen, making it more star-like than planet-like. But that definition was always incomplete. It told us nothing about formation, nothing about what these objects truly are at their core. The HR 8799 system now provides a chemical test. If you find sulfur in the atmosphere, that sulfur had to come from solids. And if it came from solids, the object built a core first. It's a planet. But wait, these monsters are pushing the upper limits. 10 Jupiter masses? Could something 15 times Jupiter's mass form the same way? 20 times? Where exactly is the transition between planet formation and something else entirely? Some researchers are already speculating that the boundary might be much higher than we thought. This could mean there are failed stars out there that we've been misidentifying as planets, and vice versa. The entire census of exoplanets might need to be revisited. And what does this mean for us? The technique used here, separating a planet's faint light from its star's overwhelming brightness, and then reading the chemical fingerprints in that light, represents the cutting edge of exoplanet science. Right now, it only works for massive gas giants far from their stars, but the researchers involved say this is just the beginning. As telescopes get bigger and instruments improve, we'll be able to apply the same methods to smaller and smaller worlds. Eventually, maybe in 20 or 30 years, we could be reading the atmosphere of an Earth-like planet, looking for oxygen, ozone, perhaps even signs of life. The smell of rotten eggs on 4 distant gas giants might seem like a strange footnote in astronomy, but it's actually a proof of concept for one of humanity's greatest questions. Are we alone? We just learned that even at these immense sizes, planets can form the same way our own gas giants did. The recipe works across different stellar systems, different conditions, different ages. Core accretion is universal, and that means the processes that built our solar system aren't unique. Here's the question that keeps me up at night. If planet formation is this consistent, if the same chemistry and physics apply across the galaxy, what else might be consistent? What other familiar patterns might we find as we look deeper into the cosmos? What do you think? Are we underestimating how common familiar planetary systems might be? Or is HR 8799 just one lucky exception? There's something almost unsettling about finding such familiar chemistry in such alien worlds. Let me know your thoughts in the comments. 20 years of mystery, solved by the smell of sulfur. Sometimes the universe's biggest secrets are hiding in the smallest details, and Webb is just getting started.